Something is out there, past Neptune, past every world we have ever directly photographed, past the frozen edge of everything we have mapped, a planet roughly 10 times heavier than Earth, on an orbit so long that a single trip around the Sun takes longer than the entire recorded history of human civilization. We have never seen it. But twice, in the same archive survey, an infrared telescope picked up faint thermal signals from exactly the region of sky it should occupy, and both times the data refused to resolve into a clean answer. 6 distant frozen worlds, scattered across hundreds of times Earth's distance from the Sun, all point through the same patch of sky. The entire planetary plane sits tipped by 6 degrees from where physics says it ought to be, and nobody has ever cleanly explained why. The pattern is real, the numbers are real, and the reason we still cannot confirm what is causing it is stranger than the mystery itself. Get comfortable, subscribe if you have not, and stay with us, because the search that has been alive for 9 years is finally about to be answered on a quiet mountain in Chile by a camera that does not get tired. Let's get into it. Part 1. The mountain high in the Andes of northern Chile, on a peak called Cerro Pachon, there is a building that looks, from a distance, like nothing more than a white dome set against a dark sky. It is 8,800 feet above sea level. The air around it is thin and dry, scrubbed of the moisture that makes most of the rest of the world's air shimmer and blur. The stars do not twinkle at this altitude. They sit very still, very bright, and very close, the way they would look to you if there were no atmosphere in the way at all. Inside that dome, mounted on a steel structure the size of a 6-story building, there is a telescope. Its primary mirror is 8.5 meters across. That is not the largest telescope in the world. There are mirrors in operation that dwarf it. What makes this particular telescope singular is what is bolted to the back of it. The camera. The legacy survey of space and time camera, the LSST camera, the largest digital astronomical camera ever constructed by human beings. You can hear the size of it in the numbers, but the numbers may not land at first, so consider this. A single image taken by the LSST camera fills a focal plane covered with 3.2 billion pixels, arranged across 189 charge-coupled devices the size of dinner plates. The patch of sky it photographs in one exposure is about 40 times the area of the full moon. If you were to display one of its raw images at the resolution it was captured at, you would need a wall of thousands of standard computer screens to see it all at once. The telescope does not stare at one target. It moves. Every 15 seconds it takes a deep exposure. Every 30 seconds it slews to the next patch. Every few nights the camera photographs the entire accessible sky. Every image is compared automatically against the last. Every point of light that has shifted between visits is flagged, and the camera will do this for 10 years. 2025 was the year the survey began. It is called the Legacy Survey of Space and Time, and the telescope is named for Vera Rubin, the American astronomer who discovered in the 1970s that galaxies rotate in a way no one could explain, and that this could only be true if the universe contained a vast hidden mass that nobody could see. There is something fitting about that. The telescope named for the woman who told us most of the universe is invisible is now turning its attention to the question of whether our own solar system contains something hidden. Because there is an argument in planetary astronomy that has been alive for 9 years, an argument about what is sitting in the outer darkness, past Neptune, past every planet we know, past every world humanity has ever directly photographed. An argument that has driven a decade of careful, patient, narrow-beam searches across an enormous and ill-defined region of sky. An argument that has been just strong enough to demand attention and just weak enough to leave the question open. The Rubin survey, by its design, ends that argument. The mirror is large enough to gather light from objects 100 times fainter than anything visible to the naked eye under perfect conditions. The cadence is wide enough that whatever orbital path a hidden distant world might be on, the camera will see it during the survey's 10-year lifetime. The strategy is unbiased. The same instrument visits the same patches of sky, at the same depth, at the same cadence everywhere, with no preference for one direction over another. This is not the kind of survey that hunts for a specific target. It is the kind of survey that simply records everything and then waits for the data to give up its secrets. You can picture it. The dome opens at sundown. The mirror, kept at a precise temperature so it does not warp under its own weight, is exposed to the cold air. The camera, cooled to about -100 degrees Celsius to suppress its own thermal noise, is ready. The first exposure is taken. The first image, hundreds of millions of points of light, flows through fiber optic cables down off the mountain to data centers around the world. While the operators on the mountain sleep, the comparisons run. Every point of light is checked against the same patch of sky as it appeared on the previous visit. Anything that has moved, anything that has appeared or disappeared, anything that has changed brightness, is flagged. The night, in other words, becomes a quietly humming machine for noticing change. Somewhere in those flagged points, eventually, may be the answer to one of the largest unresolved questions in modern planetary science. Or maybe a different answer, harder to look at directly but every bit as remarkable. That is what we are going to walk into tonight. Not all at once, slowly. Because this story has been building for a decade, and the people who built it are still working, and the answer is now closer than it has ever been, and the listener deserves the time to arrive at the question in the same shape that those astronomers arrived at it. Patiently, with increasing clarity, with the texture of how strange the data has been from the start. We're going to begin with the prediction, then with the geography of the place we are looking at, then with the marks in the data that something has been leaving. The pattern is real. The reason we still cannot confirm what is causing it is stranger than the mystery itself. Part 2. The argument that has been alive for 9 years. On January 20th, 2016, 2 astronomers at the California Institute of Technology published a paper in the Astronomical Journal. The journal volume was 151. The page was 22. The 2 authors were Konstantin Batygin and Michael E. Brown. The title of the paper was modest, almost shy. Evidence for a distant giant planet in the solar system. The paper made one specific claim. It said that the orbital motions of 6 frozen worlds in the outer solar system, 6 objects so distant that a single trip around the Sun takes them thousands of years, were too organized to be the product of random chance. The probability that the 6 bodies had ended up in their observed orbital configuration by accident was approximately 1 in 14,000. And the simplest explanation for the pattern was a single distant unseen object, a planet of around 10 times Earth's mass, moving on a long-stretched elliptical orbit somewhere between 400 and 700 times farther from the Sun than Earth is, completing one full lap every 10 to 20,000 years. A planet, in other words, that no human being had ever seen. There is a particular kind of audacity required to publish a claim like that. You're not announcing a discovery, you're announcing an inference. You're saying that an object large enough to be the 9th planet of our own solar system is implied by the math, even though no telescope has photographed it, no satellite has detected it, and no instrument has resolved its surface. You're saying that the orbits of 6 bodies you can see are bending in a way that only something you cannot see can explain. Batygin and Brown did not stumble into this. The 2 of them are well-respected scientists in their field. Michael Brown is a planetary astronomer who is, among other things, the person whose work on dwarf planets in the outer solar system led directly to Pluto being reclassified in 2006. He carries the nickname, sometimes affectionately, sometimes not, of the man who killed Pluto. Konstantin Batygin is a theorist of orbital dynamics whose work spans planetary formation, the migration of giant planets, and the long-term gravitational evolution of solar systems. Between them, they had the observational vocabulary and the dynamical machinery to take a faint statistical pattern and walk it through to a quantitative prediction. The pattern that drove the paper had been noticed before. In March 2014, almost 2 years earlier, Chad Trujillo at the Gemini Observatory in Hawaii and Scott Shepard at the Carnegie Institution in Washington had published a different paper in the journal Nature, volume 507, page 471. The Trujillo and Shepard paper announced the discovery of an object designated 2012 VP113, the second known sednoid, a small frozen world in an orbit that comes no closer to the Sun than 80 times Earth's distance, and stretches out to more than 450 times Earth's distance at its farthest point. Buried in that paper was a smaller observation. Trujillo and Shepard noted that across the handful of known extreme trans-Neptunian objects, the orientation of their orbits in space was not random. There is a number in orbital mechanics called the argument of perihelion. It describes the orientation of the elliptical orbit within its plane, specifically where the point of closest approach to the Sun sits relative to a reference direction. For a sample of random objects scattered by random gravitational chaos, the argument of perihelion should be uniformly distributed between 0 and 360 degrees. Across the small set of known extreme trans-Neptunian objects, it was clustered tightly in a narrow range. Trujillo and Shepard suggested in their paper that a perturbing object, perhaps a planet or planets at hundreds of times Earth's distance from the Sun, might be responsible. They did not predict a specific mass or orbit. They flagged the anomaly and left the door open. Battergin and Brown walked through that door. What they showed in their 2016 paper was that the clustering went deeper than Trujillo and Shepard had described. Not only the argument of perihelion was aligned across the 6 objects, so was the longitude of perihelion and the longitude of ascending node. 3 different orbital orientation parameters all aligned. The 6 objects were not just oriented similarly in the abstract, they were physically clustered in space. Their orbital ellipses were all pointing roughly the same direction, all tilted at similar angles, all bunched in roughly the same region of the sky. That kind of triple alignment is much harder to produce by chance. Battergin and Brown ran the probability calculation. The number that came out, across a sample of 6 objects this specific configuration, was around 1 in 14,000. A coincidence at that level is the kind of coincidence that science does not casually accept. It demands an explanation. It demands a mechanism. And Battergin and Brown had one. They ran n-body simulations of the outer solar system, with an added body of various masses and orbital parameters. They asked the question, in effect, what kind of unseen object could shepherd 6 independent bodies into the observed configuration and keep them there for billions of years? The answer that emerged from the simulations was specific. A planet of around 10 Earth masses, semi-major axis somewhere between 400 and 700 astronomical units, orbital inclination around 30 degrees relative to the planetary plane, a long stretched elliptical orbit reaching from somewhere around 200 or 300 astronomical units at perihelion out past 1,000 astronomical units at aphelion. A single orbit taking between 10,000 and 20,000 Earth years to complete. A planet that size in that orbit would gravitationally lock the 6 clustered objects into a kind of slow, gravitational waltz. They would not feel its pull constantly. Their orbits are so long that Planet 9, on its own slow march, would only swing through their neighbourhood once every few thousand years. But over 4.5 billion years, those rare passes would have shaped the orientations of every distant frozen body in the outer system, pulling them into the precise alignment that the data shows. The paper was published, the community noticed. The field of planetary astronomy lit up. Some scientists greeted the claim with cautious interest, others with frank skepticism. Others, including a handful of veterans of the field who had spent decades hunting for objects in the outer solar system, opened their datasets and started running their own searches. Within months, observing time on some of the world's most powerful telescopes was being requested specifically to look for Planet 9. Within a year, Infrared archives that had been gathering dust were being mined for thermal signatures consistent with what an ice giant at hundreds of astronomical units would produce. Within 2 years, dedicated optical sky surveys were combing the predicted region for a slowly drifting point of light, and nothing was confirmed. For 9 years the search continued. The predicted region of sky was vast. The brightness of any reflected sunlight from Planet 9, at 400 to 700 times Earth's distance, would be more than 30,000 times fainter than Neptune. Even with the largest available ground-based telescopes, looking for a single faint moving dot across thousands of square degrees of sky under varying atmospheric conditions with limited observing time was an extraordinarily difficult task. The search was incremental, field by field, magnitude limit by magnitude limit, year by year. And in those 9 years, the indirect evidence got more interesting. New analyses found additional anomalies in the outer solar system that the same proposed planet could naturally explain. A 6-degree tilt of the planetary plane relative to the Sun's equator, a small population of distant trans-Neptunian objects on retrograde and high-inclination orbits, subtle features in the distribution of frozen bodies past 48 astronomical units that hinted at gravitational sculpting by an unseen hand. The same 9 years also produced challenges. A team at the University of Michigan, working with data from a sky survey called the Dark Energy Survey, applied a rigorous statistical correction for the kinds of selection biases that surveys carry by their nature. Their conclusion was that, after accounting for the fact that certain orbital orientations are simply more likely to be discovered than others, depending on where and how the surveys had been pointed, the apparent clustering across the original 6-object sample was much weaker than Batajan and Brown had argued. Some statistical methods preserved a residual signal after correction. Others erased it almost entirely. The debate was real, conducted by serious scientists in good faith, and it was not resolved. And then there was the second possibility, the one that turned the search inside out. A pair of physicists at Harvard, in a paper published in 2019 in Physical Review Letters, asked a question nobody else had seriously asked. What if the object pulling on the outer solar system, the object responsible for all of the indirect evidence, was not a planet at all? What if it was a primordial black hole, a relic of the first instant of the universe, formed in the extreme density conditions of the very early cosmos before stars or galaxies existed, captured by the young solar system and sitting in the outer darkness ever since? A primordial black hole of 10 Earth masses would fit in the palm of your hand. It would emit no reflected light. It would emit no internal heat. And the indirect gravitational evidence, every piece of it, would look identical whether the object responsible was a planet or a black hole. So this is the argument that has been alive for 9 years. 6 clustered orbits, a 6-degree solar tilt, a handful of high-inclination outer system objects, a pair of faint infrared signals in a Japanese satellite archive, a new sednoid whose pristine orbit constrains where Planet 9 can be, a statistical debate about whether the pattern is real or an artifact of where humans have been looking, and hovering over all of it, the unsettling possibility that the object causing the pattern is not a planet at all. For 9 years, the question has been just answerable enough to drive a search, and just unanswerable enough to leave everyone unsatisfied. The Rubin Observatory is the experiment that settles it. That is where we are tonight. The instrument is open, the data is flowing, the patience is finally almost over. But before we go back to the mountain, we have to go further out than most people ever go. Past Mars, past Jupiter, past Saturn, past Uranus, past Neptune. We have to walk through the geography of what is actually out there, because the place we are searching is not a place anyone instinctively knows. It is the dark hall around the lit room of our familiar solar system. It is older than the lit room itself, and whatever is in it has had 4.5 billion years to leave marks. Part 3. The Geography Past Neptune. You already know the 8 planets closest to us. You learned them in school: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Most people, asked to describe the solar system, will stop there. That is the complete picture. One sun, 8 worlds, or at least that is what we have told ourselves. The solar system does not end at Neptune. It extends outward across distances that human intuition has no good way of holding. To get a feel for where the search for Planet 9 is happening, you have to walk yourself, in stages, out from where you are now into a region that has no clear edge. Start with what is familiar. Earth orbits the Sun at a distance of about 93 million miles. That distance, in astronomical conventions, is called 1 astronomical unit, 1 AU. When you sit outside on a summer day and feel the warmth of sunlight on your skin, you're receiving photons that left the surface of the Sun about 8 minutes earlier and travelled 1 astronomical unit to reach you. Now extend the picture. Jupiter orbits at about 5 astronomical units, Saturn at about 10, Uranus at about 19, Neptune at 30. Neptune is, by the standard reckoning, the outermost major planet. Its distance from the Sun is about 2.8 billion miles. From Neptune's surface, if Neptune had a surface you could stand on, the Sun would appear as a very bright point of light, brighter than any star in the sky, but 1,000 times less bright than it appears from Earth. There would be no warmth at all. The temperature at the cloud tops of Neptune is about 55 Kelvin, or about minus 218 degrees Celsius, or minus 361 degrees Fahrenheit. That is the upper limit of warmth in the outer planetary region. Past Neptune is where the search for Planet 9 begins. The first layer past Neptune is called the Kuiper Belt. The name comes from the Dutch-American astronomer Gerard Kuiper, who in 1951 published a paper speculating about a population of small frozen bodies orbiting past the outermost planet. The hypothesis sat for 40 years without confirmation until the first Kuiper Belt object, designated 1992 QB1, was discovered by a team at the University of Hawaii in August 1992. After that, the floodgates opened. Today, the catalogue of confirmed Kuiper Belt objects exceeds 3,000. Astronomers estimate there are more than 100,000 bodies in the Kuiper Belt with diameters over 100 kilometers and probably hundreds of millions of smaller ones. Pluto, the world that we used to call the 9th planet, is the largest known Kuiper Belt object. The Kuiper Belt extends from about 30 astronomical units, where Neptune is, out to about 50 astronomical units. It is shaped roughly like a thick disk, lying in the same plane as the planets, populated by objects that are mostly chunks of ice, water ice, methane ice, nitrogen ice, with smaller fractions of rock. Surface temperatures in the Kuiper Belt range from about 40 Kelvin near the inner edge down to about 30 Kelvin near the outer edge. That is cold enough that nitrogen, which on Earth is a gas in our atmosphere, freezes solid on the surfaces of Kuiper Belt objects. If you were to stand on the surface of a Kuiper Belt object, pick one, say Pluto, where the New Horizons spacecraft flew past in 2015 and gave us our first clear photographs, the Sun would shrink even further. From Pluto, the Sun is roughly 1,300 times less bright than it is from Earth. It still casts shadows. You can read by its light. But it is not the warm yellow disk you see from Earth. It is a small, intensely bright point, like a welding arc seen from a long way away, casting a faint blue-white illumination on a world made of ice mountains and methane snow. At about 48 astronomical units, the population of Kuiper Belt objects falls off sharply. Astronomers call this the Kuiper Cliff. The standard model of solar system formation does not predict a cliff. It predicts a gradual thinning, like the edge of a forest where the trees become more scattered before stopping. What we see instead is more like the edge of a clearing. Bodies are abundant inside 48 astronomical units. They become rare past that, in a way that no model has cleanly explained. Some astronomers have suggested the cliff is evidence of a past gravitational disturbance that sculpted the outer edge of the Kuiper Belt early in the solar system's history. Some have suggested it is a true edge to the original protoplanetary disk from which everything formed. Some have suggested it is a sampling effect, that smaller and dimmer objects past 48 astronomical units are simply too hard for our telescopes to detect. We do not know. The cliff is part of the unexplained landscape past Neptune. Past the cliff is a region called the scattered disk. The scattered disk is sparser than the Kuiper belt, and the objects in it move on long, stretched, often inclined orbits, whose closest approaches to the Sun still bring them near Neptune's gravitational reach. Bodies like Eris, the largest known scattered disk object, swing in on orbits that take hundreds of years to complete and reach out past 90 astronomical units before turning around. The scattered disk is, in a sense, a graveyard of objects that Neptune long ago kicked outward and that have been making slow eccentric circuits ever since. Past about 100 astronomical units, the population thins again, and here you enter the region where the search for Planet 9 takes place. This is the extreme trans-Neptunian zone. The orbital periods get longer, the objects get rarer, and the orbits begin to do something strange. In 2003, a team led by Michael Brown at Caltech, with Chad Trujillo and David Rabinowitz, discovered an object that did not fit any of the existing categories. It was officially designated 90,377, but it received an unofficial name from Inuit mythology, Sedna, the goddess of the sea, the keeper of the cold deep. Sedna's orbit is unlike anything previously found. Its closest approach to the Sun is 76 astronomical units. Its farthest distance is 937 astronomical units. A single orbit takes approximately 11,400 Earth years to complete. Sedna takes longer to circle the Sun than the entire recorded history of human civilization. And here is what made Sedna important. Its closest approach is too far from Neptune for Neptune's gravity to have placed it there. Neptune's gravitational reach effectively ends well inside 70 astronomical units. There is no mechanism in the standard model of solar system formation that delivers an object into Sedna's orbit. Whatever pushed Sedna out to that distance and left it there had to be something else. Several theories were proposed. A passing star early in the Sun's life, when the Sun was still embedded in its birth cluster, might have dragged Sedna out. A massive perturber, sitting somewhere in the far outer solar system, might have lifted Sedna's orbit. Some combination of the two might have done it. Nobody had a clean answer. Sedna sat in the catalogues as a beautiful and unresolved anomaly. Then more sednoids were found. In 2014, Trujillo and Shepard published the discovery of 2012 VP113, a second sednoid with an even more extreme orbit, perihelion at about 80 astronomical units, and aphelion past 450. In 2018, a third object was added, Lekuhonua, also known by the unofficial nickname the Goblin, with a perihelion near 65 astronomical units. And in 2023, a fourth sednoid was discovered by a Japanese-led survey at Mauna Kea using the Subaru telescope, 2023 KQ14, with a perihelion of about 71 astronomical units and an aphelion past 800. 4 sednoids. 4 objects on extraordinarily stable, extraordinarily long-period orbits, each one moving in a region of the solar system that no standard formation model produces, each one requiring an explanation for how it ended up there, and each one stable enough to suggest that whatever pushed them out had since retreated to a comfortable distance, because nothing was disturbing them now. Now extend the picture one final step, past the sednoids, past the extreme trans-Neptunian zone, somewhere between a few thousand and perhaps 200,000 astronomical units from the Sun, lies the Oort cloud. The Oort cloud is named for the Dutch astronomer Jan Oort, who proposed its existence in 1950 based on the orbital distribution of long-period comets. We have never directly imaged the Oort cloud. Its existence is inferred entirely from cometary statistics, from the fact that long-period comets enter the inner solar system from random directions in the sky, with orbital periods consistent with origins thousands, to tens of thousands of astronomical units away. The Oort cloud is thought to contain roughly 1 trillion icy bodies arranged in a vast spherical shell wrapping around the entire solar system. The outer edge of the Oort cloud, at perhaps 150,000 to 200,000 astronomical units, is roughly halfway to the nearest other star. The Sun's gravitational reach effectively ends there. Past the Oort cloud is interstellar space. That is the geography. Inside 30 astronomical units, the well-lit planetary region we grew up learning about. Past Neptune, layers of cold and slowly moving material extending across hundreds, then thousands, then tens of thousands of astronomical units. The Kuiper belt, the scattered disk, the sednoid zone, the Oort cloud, and in the middle of all that, somewhere in the extreme trans-Neptunian region between 200 and 1,000 astronomical units, the predicted location of Planet 9. The scale takes a moment to absorb. Light from the Sun takes about 8 minutes to reach Earth. It takes about 4 hours to reach Neptune. It would take more than 2 days to reach Planet 9 at its predicted distance. A spacecraft travelling at the speed of New Horizons would take more than 700 years to reach the inner edge of the Oort cloud, and more than 30,000 years to reach the outer edge. The inner solar system, the part we know, the part where life evolved, is a small lit room. Around it, in every direction, is an enormous dark hall. The dark hall is older than the lit room. Most of the material the Sun gathered up when it formed went into the dark hall, not into the room, and inside that dark hall something has been organising the orbits. For 9 years, the best evidence we have had for what that something is has been a pattern. A pattern in the orbits of 6 distant frozen worlds. A pattern that, if it is real, points to a single hidden object. A pattern that, if it is an artifact of how we have been looking, points to nothing at all. We have to look at the pattern itself, carefully, because everything that follows depends on what the pattern is and on how confident we can be that the pattern is really there. Part 4. 6 compass needles. Imagine, for a moment, that you're standing at a long wooden table in a dim room. The table has been carefully cleaned. Its surface is flat. You have 6 sticks, of roughly equal length, scattered across the room. Your task is to drop the sticks onto the table, one at a time, from different heights and at different angles. You drop the first stick. It lands somewhere on the table, pointing in some direction. You drop the second. It lands in a different place, pointing in a different direction. You drop the third, the fourth, the fifth. Each one lands somewhere on the table, pointing somewhere. The angles are random. The positions are random. After 6 sticks, you have a small messy collection of 6 pieces of wood, oriented in 6 different ways, scattered across the surface. That is what gravity is supposed to produce, in the orbits of distant frozen worlds, after 4.5 billion years of random scattering. Now imagine you drop the same 6 sticks, again, and every single one of them lands pointing the same direction. Imagine you drop them twice more, 6 at a time, and each time, every single stick comes down, pointing the same way. You would not call that coincidence. You would start looking for whatever was pointing them. That is what Konstantin Batygin and Michael Brown found in 2016. 6 independent objects in the extreme outer solar system. 6 orbits, each one a long stretched ellipse, each one taking thousands of years to complete. The orbits do not have to share any particular orientation. Gravity, over billions of years, would scatter them in every direction, the same way the dropped sticks should land in every direction. The 6 observed orbits all pointed the same way. The technical language for this is precise. Each orbit has 3 orientation parameters in 3-dimensional space. The argument of perihelion describes where the closest approach to the Sun sits relative to a reference direction within the orbital plane. The longitude of ascending node describes where the orbit crosses the reference plane. The longitude of perihelion combines the two and describes the orbital orientation as projected onto a fixed direction in the sky. For a random population, each of these 3 parameters should be uniformly distributed across the full possible range. Across the 6 objects Batygin and Brown studied, all 3 parameters were clustered. The 6 perihelia, the 6 points of closest approach to the Sun, were physically clustered together in the same region of space. The 6 orbital planes were tilted at similar angles, also clustered, and the 6 orbits, viewed from outside the solar system, all swept through the same region of the sky. The mathematical question, then, was the same as the question of the dropped sticks. What is the probability of getting all of that alignment by chance? Batygin and Brown ran the calculation carefully. They used a sample of the most distant, most dynamically isolated objects available, the ones whose orbits are not being actively perturbed by Neptune, the ones whose orientations should be a frozen record of whatever forces shaped them in the past. They corrected for the fact that the available sample was small. They accounted for the orbital integrations across billions of years that should naturally tend to randomize the orientations through diffusive processes. The answer they got was a probability of about 1 in 14,000. The probability that 6 independent objects in the outer solar system would, by random chance, share the orbital orientations that the data showed was approximately 0.07%. That is not a confirmation of anything. The history of astronomy is full of patterns that turned out to be coincidences after more data became available. 1 in 14,000 is also not so small that you can simply rule out a chance fluctuation across the unimaginable number of statistical tests that have been performed in the history of planetary science. But it is small enough that the responsible scientific response is to ask whether some unseen physical mechanism could be responsible. So Batygin and Brown asked. They built numerical models of the outer solar system, dropped in a hypothetical massive object on various orbits, and asked whether any combination of mass and orbital parameters could produce the observed clustering and sustain it over billions of years. The simulations were not subtle. A perturber of around 10 Earth masses on a long elliptical orbit at hundreds of astronomical units, inclined by about 30 degrees relative to the planetary plane, produced a kind of slow gravitational shepherding of the distant trans-Neptunian objects. Over the age of the solar system, the proposed planet would pass through the neighbourhood of the clustered objects on its slow orbital march, and each pass would gently nudge their orientations toward alignment with its own orbit. The math worked. The alignment was stable. The clustering pattern produced by the simulations matched the observed pattern across the 6 original objects. There is a particular kind of physical intuition that goes with results like this. In the same way that a single large boulder dropped into a quiet pond produces a coherent ripple pattern that spreads outward over time, a single large planet dropped into a population of distant frozen bodies produces a coherent alignment pattern in their orbits over billions of years. The orbit of each individual body is being nudged slowly and subtly by an invisible source that has been present for the entire history of the system. The texture of that, when you sit with it, is striking. 6 independent worlds, separated by hundreds of astronomical units, moving on orbits that take thousands of years to complete, are all in some sense responding to the same unseen presence, pulled by the same hand, aligned by the same force. The force itself is faint enough that you cannot feel it directly. It is detectable only by its statistical fingerprint across an entire population of objects. Picture the 6 sticks again. Picture them landing on the table, each one pointing the same direction. Picture the table not as a table but as a region of space across hundreds of times Earth's distance from the Sun. Picture the sticks not as sticks, but as the trajectories of frozen worlds, each one moving so slowly that an entire orbit takes longer than recorded human history. Picture them all pointing the same way. That is the pattern. Something is pointing them. We have called the something planet 9 for now, because the simplest interpretation of the pattern is that it is being made by a single large unseen object in a particular orbit. But we have to hold that label gently, because as we'll see, the something is not necessarily a planet. The same alignment can be produced by other things, some of them stranger than a planet. But before we get to the alternatives, we need to look at the second mark. because the 6 clustered orbits were not the only piece of indirect evidence that something was out there. There was another anomaly sitting in the textbooks for decades that nobody had ever satisfactorily explained. And when Batterjin and Brown asked whether their proposed planet could account for that one too, the answer they got was, more cleanly than they had any right to expect, yes. The 6 compass needles all pointing the same way are not just a story about 6 orbits. They're a story about how an unseen object has been quietly composing patterns in our solar system since before the planets settled into their current orbits. And the next pattern goes all the way down to the angle at which the planets themselves orbit. Part 5. The tilt. Nobody could explain. Every planet in the solar system orbits the Sun in roughly the same flat plane. This is one of the first things you learn about the structure of the solar system, and it is one of the deepest features of how solar systems form. The planets did not pick their orbital plane independently. They inherited it from the protoplanetary disk, the rotating, flattening cloud of gas and dust from which the Sun and all of its planets formed about 4.5 billion years ago. When a cloud of gas and dust collapses under its own gravity, conservation of angular momentum forces it to flatten. Any small initial rotation in the cloud gets amplified as the cloud contracts, in the same way that a figure skater pulling in their arm spins faster. The original 3-dimensional volume of the cloud collapses into a thin 2-dimensional disk, spinning around a central axis. The Sun forms at the centre of the disk, gathering most of the mass. The planets form from the remaining material in the disk itself, settling into orbits that lie within the disk as plane. This is not theory. We watch it happen around other young stars. Modern telescopes have photographed protoplanetary disks around hundreds of newborn stars across the Milky Way. The disks are visibly flat, visibly rotating, visibly producing planets that orbit within their own plane, which means that the plane the planets orbit in should be aligned with the rotation of the central star. Both are inheriting the same angular momentum from the same original cloud. The Sun's equator and the plane of the planets should match. They do not. The Sun's equatorial plane and the plane that the planets orbit in are not the same plane. They are offset from each other by approximately 6 degrees. 6 degrees is not a small angle in astronomical terms. It is large enough to be measured precisely. It is large enough that no rounding error or measurement uncertainty can account for it. The tilt has been known for many decades, refined by every subsequent generation of solar observations and planetary orbital calculations, and it has not been satisfactorily explained. Let me say more about what that tilt actually looks like, because the word tilt can be slippery. If you imagine the Sun as a spinning ball, with a clear axis running through its north and south poles, and a clear equator running around its middle, then the equator defines a flat plane. Now imagine the orbits of the planets as a separate flat plane, the orbital plane, tilted slightly relative to the Sun's equator. The two planes meet along a single line, but otherwise they do not coincide. The angle between them, the dihedral angle as a mathematician would say, is 6 degrees. 6 degrees across 8 planets, every one of them. This is not a quirk of one planet. It is not a feature that only shows up in Pluto's orbit, or only in the asteroid belt. It is a tilt of the entire planetary system relative to the Sun's own spin. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. All of them are sitting in a plane that is 6 degrees off from where you would expect them to be. For decades, this tilt sat in the textbooks as a known but unexplained feature. There were proposals. A passing star, very early in the solar system's life, might have tugged the protoplanetary disk by gravity and tipped it relative to the young Sun's spin axis. A primordial misalignment between the Sun and its disk, present from the moment of formation, might never have been corrected. The Sun's own internal magnetic dynamics might have interacted with the disk in a way that misaligned the two. Stochastic torques during the chaotic final stages of planet formation might have done it. None of these proposals produced a clean quantitative match to the observed 6 degrees without significant fine-tuning. Each of them required adjusting parameters by hand to get the numbers to come out right. Each of them carried its own assumptions about events that happened 4.5 billion years ago, events for which we have no direct record. So the tilt sat there, a real, measurable, persistent anomaly, sitting in the data, in plain view, since the days of Galileo, waiting for an explanation that did not feel forced. In October 2016, 8 months after Batygin and Brown's original Planet 9 paper, a young astronomer named Elizabeth Bailey, a graduate student at Caltech working with Batygin and Brown, published a paper in the Astronomical Journal, volume 152, page 126. The title of the paper was direct: Solar Obliquity Induced by Planet 9. What Bailey, Batygin and Brown showed in that paper was that a planet of around 10 Earth masses on a long inclined orbit at hundreds of astronomical units would, over the 4.5 billion year lifetime of the solar system, exert a slow gravitational torque on the entire population of inner planets. The torque would not be sudden. It would not produce any single dramatic event. It would be the kind of force that, applied gently and continuously across geological time, would walk the orbital plane of the planet slightly away from its original alignment with the Sun's equator. The torque is real physics. Any massive body on an inclined orbit gravitationally interacting with the planets produces secular torques that slowly precess and tilt the planetary plane. The question is whether the magnitude of the torque integrated across the age of the solar system produces a final tilt that matches the observed value. Bailey ran the integrations. The answer that came out of the calculation was within the observed range, approximately 6 degrees, give or take, with the exact number depending on the precise orbital parameters of the hypothetical planet. The model did not require fine-tuning. It did not require lucky initial conditions. It simply required the planet to exist on the kind of orbit that the clustering analysis had independently predicted. 2 independent anomalies, 2 independent puzzles, 1 proposed planet that accounts for both. This is the kind of result that, in science, changes the texture of a question. A single anomaly with a single proposed explanation is interesting but easy to set aside. 2 anomalies, found independently, in different parts of the solar system, on different timescales, both naturally produced by the same model, that is something else. That is not a hypothesis that you can easily dismiss as a one-off coincidence. That is a hypothesis that has started to make multiple predictions that match multiple observations, which is the texture of a hypothesis that may be tracking something real. Sit with the second anomaly for a moment, because it is worth feeling. The tilt has been visible since the invention of astronomy. Every star chart drawn by every ancient astronomer recorded planetary positions along an orbital plane tilted 6 degrees from where it should have been. Every painting of the night sky from antiquity, every observation log from medieval Arabic and European astronomy, every photograph of the planets taken across the 20th and 21st centuries, every observation by Galileo through his first telescope, every measurement by Tycho Brahe and Johannes Kepler, every calculation that built the foundation of modern celestial mechanics. The tilt has been there the whole time, 6 degrees, silently, across every observation humanity has ever made. It is in every star map you have ever seen. It is in every astronomical photograph in any book you have ever opened. It is in every clear night sky you have ever stepped outside under, in the angle at which the planets sit relative to the position of the Sun on the celestial sphere. If Planet 9 is real, then the tilt is the planet's fingerprint pressed across the entire history of human stargazing. Every time anyone has looked up at the night sky and traced the path of a wandering planet across the constellations, they have been looking along a plane that was tipped, ever so slightly, by something they could not see. The handiwork of the unseen planet has been written in plain view for thousands of years, and it took us until 2016 to begin to recognize it. There is a particular weight to that. It is not the weight of discovery. It is the weight of recognition. The realization that an anomaly which has been visible to anyone with eyes and patience for the entire history of astronomy was a signature of something we had not learned how to read until very recently. The planet, if it is there, has been signalling to us continuously since before human beings existed. This signal has been in our data. We just did not know how to interpret it. So now we have two pieces of evidence. The orbital clustering of 6 distant frozen worlds, the 6 compass needles all pointing the same way, and the 6-degree tilt of the entire planetary plane, the fingerprint that has been visible across the entire history of stargazing. Both of them naturally produced by a single model, both of them pointing to the same unseen object. There are other pieces too, smaller anomalies that the same proposed planet can account for. A small population of trans-Neptunian objects whose orbits run backwards through the solar system, retrograde to the planetary motion, at high inclinations approaching or exceeding the perpendicular. Standard formation models do not produce these in the observed numbers. Battagin and Alessandro Morbidelli showed in 2017 that a long-inclined Planet 9 would naturally lift some scattered disk objects into high inclination and retrograde orbits via secular resonance interactions across billions of years. The retrograde objects are a third independent line of indirect support. Other proposals exist for individual pieces of the puzzle, but no single alternative explains all three at once. The case for Planet 9, by the time the indirect evidence had accumulated, was made of 3 or 4 converging anomalies, all of which the same model could naturally produce. None of them, by itself, would be conclusive. Together, they were strong enough to make the search for the planet one of the largest and most expensive efforts in modern planetary astronomy. But indirect evidence is indirect for a reason. The case had been built without ever seeing the object that the case argued for. Every piece of the case could be matched in principle by other explanations. An unusual statistical fluctuation, a primordial misalignment, a chance encounter with another star, a flaw in the way our surveys had collected the data. The only way to settle the question was to find the planet itself, and finding the planet itself was, it turned out, going to be much harder than anyone expected. Because reflected sunlight, the way every other planet in the solar system has been discovered, was not going to be enough. Not at the distances Planet 9 was predicted to occupy. The math of how light falls off with distance was about to become a serious problem. Part 6. Why light will not find it. There is a small piece of physics that decides why this search has been so difficult, and it is worth taking a moment to look at it clearly. When sunlight leaves the surface of the sun, it spreads outward in all directions, weakening as it goes. The weakening is governed by what is called the inverse square law. Move twice as far from the sun, and the amount of sunlight per unit area falls by a factor of 4. Move 10 times as far, and the sunlight falls by a factor of 100. That is the first weakening. The light has to travel from the sun to the planet. Now the light hits the planet. Some of it is absorbed and warms the planet. Some of it is reflected back into space. The reflected light is what your eye sees when you look at Jupiter or Saturn in the night sky. Sunlight bouncing off the cloud tops and travelling back to your eye on Earth. But the reflected light, once it leaves the planet, has to travel back to your telescope. And that journey is also governed by the inverse square law. The reflected light spreads out from the planet in all directions, weakening by another factor of distance squared as it travels back across the solar system. So the total amount of reflected sunlight that reaches your telescope from a distant planet depends on the inverse 4th power of the planet's distance from the sun. The first factor of distance squared accounts for how much sunlight reaches the planet in the first place. The second factor of distance squared accounts for how much of the reflected light makes it back to Earth. That is a brutal scaling. A factor of 4th power is one of the steepest scaling laws in physics. Move a planet 10 times farther away, and the reflected light you can collect from it falls by a factor of 10,000. Move it 100 times farther, and the reflected light falls by a factor of 100 million. Now let's apply that scaling to the search for Planet 9. Neptune orbits at about 30 astronomical units from the Sun. Neptune is, by the standards of the inner solar system, very faint. Through a small telescope it appears as a pale blue dot. several magnitudes fainter than the dimmest star you can see with the naked eye. Even a modest backyard telescope has to be carefully aimed to find it. Planet 9 is predicted to sit somewhere between 400 and 700 astronomical units from the Sun. That is between 13 and 23 times farther away than Neptune. Apply the inverse fourth power. The reflected light from Planet 9 compared to Neptune would be fainter by a factor between 13 to the fourth and 23 to the fourth. Run the numbers. 13 to the fourth is about 28,000. 23 to the fourth is more than 280,000. So Planet 9, in reflected sunlight, would be somewhere between roughly 30,000 times fainter and 250,000 times fainter than Neptune, depending on where exactly it sits in its orbit. To search for an object that faint by reflected light, your telescope has to do two things at once. First, it has to be sensitive enough to pick up the faint signal against the background of the night sky. That requires a large mirror to collect a lot of photons and a long exposure time to integrate the signal. Second, it has to know where to look. A faint object spread across a wide search area requires either an enormously sensitive instrument covering all of the area, or a very precise prediction of the small region the object actually sits in. For 9 years, the search community has been working both sides of this problem. Specific telescopes have been pointed at specific predicted positions using the latest refinements of the Planet 9 orbital model. Long exposures have been taken. Faint candidates have been flagged and followed up. None of the resulting candidates has survived the scrutiny. And the search keeps running into the same difficulty. At hundreds of astronomical units, in reflected sunlight, Planet 9 is simply at the edge of what current ground-based telescopes can plausibly detect, with reasonable observing times across the relevant area of sky. Some specific candidate positions have been ruled out. Most of the orbit has not been definitively searched. The needle is small, the haystack is vast. But there is another way to look, and the other way does not depend on reflected sunlight at all. Every planet of any significant mass leaks energy. This is not optional. It is a direct consequence of how planets form and how they hold themselves together. When a planet first accretes from the protoplanetary disk, its material is gravitationally collected from a much larger volume. The collapse from the disk to the compact planet releases gravitational potential energy as heat. That heat does not disappear. It is stored in the interior of the planet, and it leaks slowly outward over billions of years through the planet's surface as thermal infrared radiation. Other heat sources contribute too. Radioactive decay of unstable isotopes in the planet's interior, particularly uranium, thorium, and potassium-40, generates ongoing heat over geological timescales. Gravitational settling of denser materials toward the planet's core releases additional potential energy. Tidal interactions with other bodies when present can add yet more. The total amount of heat a planet leaks depends on its mass and its formation history. For Earth, the geothermal heat flow is small compared to the sunlight Earth absorbs, but it is real and measurable. For Jupiter, the internal heat flow is large enough that Jupiter radiates approximately 1.67 times as much energy outward as it absorbs from the Sun. For Neptune, the same number is roughly 2.61. Neptune radiates more than 2.5 times as much energy as it receives from sunlight. Neptune is in some sense its own faint heat source. For an ice giant of roughly 10 Earth masses sitting at 400 to 700 astronomical units from the Sun, the math works out cleanly. The amount of sunlight reaching the planet is negligible. The temperature of the planet is set almost entirely by its own internal heat. Different models give somewhat different predictions, but the surface temperature is generally expected to be in the range of about 30 to 50 Kelvin, roughly minus 240 to minus 220 degrees Celsius. Very cold by Earth standards, but warm enough to glow detectably in the far infrared portion of the spectrum, at wavelengths around 50 to 200 micrometers. And here is the crucial part. The thermal emission from the planet does not suffer from the inverse fourth power problem. The reflected light suffers from the fourth power because both the light arriving at the planet and the light leaving the planet are governed by the inverse square law. But thermal radiation from the planet itself is generated at the planet. It does not have to travel from the Sun first. It only has to travel back to your telescope, which is governed by the inverse square law alone. So while reflected sunlight from Planet 9 falls off as the inverse fourth power, the planet's own thermal infrared emission falls off only as the inverse second power. That is a much less brutal scaling. At hundreds of astronomical units, the thermal signal from Planet 9 is still very faint by absolute standards, but it is not nearly as devastatingly diluted as the reflected light would be. A sensitive enough far infrared detector, looking in the right wavelength band, could in principle pick it up. There is a complication. Far infrared radiation is extremely difficult to observe from the ground. Earth's atmosphere absorbs almost all far infrared light before it reaches a ground-based telescope. The wavelengths you actually want to look at can only be observed from above the atmosphere, which means from a satellite or a spacecraft. There is a second complication. A far infrared detector that is itself warm, sitting at room temperature for example, would generate enormous amounts of its own infrared light, drowning out any signal from a distant cold planet. The detector has to be cooled, ideally to within a few degrees of absolute zero, so that it radiates almost no infrared light of its own. Cooling a detector to those temperatures requires liquid helium or sophisticated mechanical refrigerators. The technology exists. It is expensive, it is delicate, and the resulting telescopes have limited operating lifetimes because they run out of coolant or refrigerant fuel. But the technology does exist, and one such instrument, a Japanese satellite called Akari, completed a full all-sky survey at the relevant wavelengths in 2007, while its liquid helium supply was still cooling its detectors. The data from that survey is publicly available. In 2025, a team of astronomers led by Terry Long-Fan at National Tsinghua University in Taiwan, working with colleagues at the Japanese Space Agency and other institutions, finished cross-referencing the Akari Far Infrared Archive against the predicted orbital arc of Planet 9, and what they found was unexpected. They found two candidates. Part 7, Akari. The Japanese Akari satellite was launched on the 21st of February 2006 from the Uchinura Space Center in southern Japan. It carried a single instrument bay mounted at the back of a 68-centimeter primary telescope mirror that was equipped to observe in the far infrared portion of the spectrum at wavelengths from 60 to 160 micrometers. The entire telescope assembly was wrapped in a cryostat containing liquid helium, kept at around 6 Kelvin, close to the temperature at which helium itself liquefies, and almost as cold as it is physically possible to make a piece of hardware in space. The cold matters. At room temperature, every surface of the telescope would emit enormous quantities of its own far infrared radiation, swamping any signal from a distant cold object. Cooling the telescope to 6 Kelvin reduces its thermal background to a negligible level, allowing the detectors to register the faintest infrared signals from across the universe, including from very cold distant objects in the outer solar system. Akari's primary scientific mission was not to find Planet 9. It was to produce the first all-sky survey at far infrared wavelengths since the IRAS satellite had completed its survey in 1983. The far infrared sky as seen by Akari was a window into galactic dust, into the warm interstellar medium, into star formation regions, into distant infrared bright galaxies. Across the 18 months that Akari's liquid helium supply lasted, the satellite mapped the entire sky twice in the far infrared. Its catalogue of bright far infrared point sources was made publicly available in 2010, with subsequent refinements. For more than a decade after that, the Akari catalogue sat there, public and accessible to anyone with the patience to query it. Thousands of researchers used it for thousands of projects. None of them, until 2024, asked it the specific question that Fan and his collaborators decided to ask. The question was simple in concept. Take the Akari Far Infrared catalogue. Take the predicted orbital arc of Planet 9, the swath of sky in which Planet 9, given the constraints from Batterjee and Brown's clustering analysis, could plausibly be sitting. Cross-reference the two. For every Akari source within the predicted arc, check whether it has a known counterpart in any published catalogue of stars, galaxies, asteroids, or other known minor bodies. Eliminate everything with a known identity. See what is left. The process was methodical and slow. The Akari catalogue within the relevant region of sky contained thousands of point sources. Each one had to be checked against the major published star catalogues. Each one had to be checked against the Gaia astrometric catalogue, which contains positions for more than 1 billion stars across the sky. Each one had to be checked against the major published catalogues of galaxies, including the SDSS Galaxy catalogue and various deep field surveys. Each one had to be checked against the Minor Planet Center catalogue of known asteroids and comets, and other small bodies. Anything with a clear identity was eliminated. The list shrank, source by source, from thousands to hundreds, from hundreds to dozens, from dozens to a handful. 2 sources remained. 2 points of far infrared light, both within the predicted orbital arc of Planet 9, both with no identified counterpart in any of the major catalogues of known objects. Each one had been picked up by Akari's detectors as a real source above the noise threshold, in the right wavelength band, at brightnesses consistent with what an ice giant of around 10 Earth masses at several hundred astronomical units would produce. That on its own would have been suggestive, but it would not have been definitive. There are many possible sources of unidentified far infrared light. A previously uncatalogued background galaxy, a faint Milky Way object missed by surface density surveys, an artifact of the Akari detector pipeline. Each of these can produce a real point source in the catalogue without corresponding to anything in the outer solar system. What made the 2 candidates more interesting was their behaviour across time. Fan and his colleagues did not stop at the Akari catalogue. They went back to IRAS, the older infrared astronomical satellite that had completed its all-sky infrared survey in 1983, 23 years before Akari. The IRAS catalogue covers the same parts of the sky as Akari does, at lower angular resolution and different wavelengths, but with enough sensitivity to detect a hypothetical Planet 9 if it was bright enough in the infrared and was within the IRAS sensitivity range. For each of the 2 surviving candidates, the team compared the Akari position to the IRAS position from 23 years earlier. A distant galaxy, or a faint background star, if visible in both surveys, should appear at almost exactly the same position in both. Background sources do not move appreciably against the celestial sphere on 23-year timescales. The proper motions of nearby Milky Way stars are typically tiny over that interval. Distant galaxies essentially do not move at all. A solar system object, however, would move. An object at 400 to 700 astronomical units from the Sun, on its slow orbital march, would shift its position in the sky by some amount over 23 years. The exact amount depends on the object's distance and the geometry of its orbit, but for a Planet 9 candidate at the predicted distances, the expected positional drift between the IRAS observation in 1983 and the Akari observation in 2006 should be a small but detectable number of arc minutes. The 2 surviving candidates both appeared to have shifted. Picture the room in which someone notices that. It is 2024. Fan and his collaborators have been working through the Akari catalogue for months. The cross-referencing is detailed and meticulous. The list has been narrowing. They have run the IRAS comparison on the 2 remaining candidates. The output of the comparison is on the screen. It shows that both candidates have apparent positional shifts in the right direction and at roughly the right magnitude for objects at the predicted distance of Planet 9. In a room somewhere in Taiwan or Japan, a person sitting at a workstation is looking at 2 points of infrared light that may be the most consequential planetary discovery since 1846. Or may turn out to be background contamination. They do not announce anything. They cannot. The data does not yet support a confirmation. The Akari candidates have passed an internal filter, but they have not been verified by independent follow-up observations. Akari's spatial resolution at the relevant far infrared wavelengths is limited. around 30 arc-seconds, which is broad enough that the candidates could be faint background galaxies sitting just below the detection threshold of the deeper catalogues the team cross-referenced against. The apparent positional shifts, while suggestive, are at the edge of what the combined Akari and IRA's precision can resolve. The team writes up the result carefully. They publish in April 2025. They are explicit about what they have found and what they have not found. They report 2 infrared sources in the predicted orbital arc that survive cross-elimination with published catalogues. They report apparent positional shifts consistent with Planet 9 drift. They note the angular resolution limitations of Akari. They call for independent follow-up observations at higher resolution to confirm or eliminate the candidates. The astronomical community responds. Several independent groups attempt follow-up observations. Some searches do not detect anything at the candidate positions. Others detect something faint, but cannot establish whether the source has moved between epochs. Movement, the critical test that would separate a solar system object from a background galaxy or star, requires precise position measurements at multiple epochs, and the precision required is at the limit of what the available follow-up instruments can deliver. As of 2025, neither candidate has been confirmed as Planet 9, and neither has been ruled out as background contamination. They sit in an uncomfortable middle ground, not confirmed, not eliminated, not explained. The unsatisfying nature of that limbo is itself worth sitting with. There is a particular kind of frustration in observational astronomy when the data is suggestive but inconclusive. You have something. You cannot say what it is. The signal is real, in the sense that Akari's detectors registered a real flux of far-infrared photons from those positions. The interpretation of the signal is not. The same data is consistent with a distant cold planet and with a distant background galaxy that happens to share certain spectral and positional properties. What the Akari search has established, even without a confirmed detection, is something important. The thermal infrared method works. The far-infrared all-sky survey approach can find candidates within the predicted region. The signal Planet 9 would produce is not below the noise floor of the technique. Every piece of data, even ambiguous data, narrows the predicted search region by adding information about where the object plausibly is or is not. The 2 Akari candidates gave researchers a more specific neighbourhood to focus on. Not a confirmed address, but a narrowed neighbourhood. In a search across billions of cubic miles of darkness, narrowing the neighbourhood is everything. There is a second consequence. The Akari results strengthen the case for pointing more powerful instruments at the candidate positions. The James Webb Space Telescope, the largest and most sensitive space observatory ever launched, has the infrared capability in principle to detect a Planet 9-sized object at the predicted distance range. But JWST does not survey the sky. It stares at specific targets. Pointing it at a vast undefined search zone is not a viable strategy. Pointing it at a narrowed neighbourhood is. The Akari candidates, even unconfirmed, gave the field a starting point for targeted JWST observations that would not have existed otherwise. The candidates are out there. They are real points of infrared light, sitting in a public archive that anyone with a laptop can download. One of them might be a planet. One of them might be a primordial black hole. One of them might be a previously uncatalogued background galaxy. Nobody yet knows which. The data has been sitting there since 2007, waiting for someone to ask it the right question, and that question is still being asked. While the Akari question was being asked, however, another piece of evidence arrived from a completely different direction. Not from a satellite, from a telescope on the ground, on top of a mountain in Hawaii, searching the outer solar system with a different strategy. The discovery was a new sednoid, and its orbit was about to complicate the Planet 9 story in a way nobody had anticipated. Part 8, 2023 KQ-14 and the Quiet Orbit. The Subaru telescope sits at the summit of Mauna Kea on the Big Island of Hawaii, at an elevation of just over 4,200 meters, more than 13,700 feet above sea level. Its primary mirror is 8.2 meters across, one of the largest single-piece astronomical mirrors in operation. The telescope is owned and operated by the National Astronomical Observatory of Japan. For the past several years, a survey called the Formation of the Outer Solar System, an icy legacy survey, or FOSSIL for short, has been using the Subaru telescope's Hyper-Suprime Cam wide-field imager to map the population of small bodies in the outer solar system. The survey is designed to find objects that are too faint and too distant to have been previously catalogued. It works by taking deep, wide-field images of patches of sky near the ecliptic, comparing the images across multiple nights to look for objects that have moved, and following up promising candidates with additional observations to refine their orbits. In 2023, the FOSSIL survey discovered a new object. The provisional designation it received was 2023 KQ-14, after follow-up observations across the next 2 years, including data from multiple telescopes around the world. A team of astronomers led by Yukun Huang at the National Astronomical Observatory of Japan published a detailed characterization of the object in 2025. What they found was in some ways exactly the kind of object the Planet 9 search community had been hoping for. 2023 KQ-14 turned out to be a sednoid, a member of that rare category of frozen worlds whose orbits never bring them close enough to Neptune for Neptune to be the perpetrator of their dynamics. Its closest approach to the Sun, its perihelion, is approximately 71 astronomical units. Its farthest distance, its aphelion, extends past 800 astronomical units. A single orbit takes more than 10,000 Earth years to complete. This made it the fourth known sednoid, joining Sedna, 2012 VP113 and Leleku Honua. And, like the other sednoids, 2023 KQ-14 was an object on a stable, very distant, very long period orbit, entirely beyond Neptune's gravitational reach. A new data point in a small but growing population, and the population mattered for Planet 9. The sednoids are part of the same family of distant objects whose orbits Batygin and Brown had argued were being shaped by an unseen planet. Each new sednoid was another test of the Planet 9 hypothesis. Each new orbit was a new piece of information about what an unseen perturber had or had not been doing in the outer solar system. 2023 KQ-14's orbital orientation passed the first test cleanly. It pointed in the same general direction as the other clustered objects. The compass needle still pointed the same way. The pattern that had motivated the Planet 9 search was not contradicted by the new arrival. It was confirmed. But there was a second test, and that one was less straightforward. The second test involved the precision of the orbit. The Subaru/FOSSIL survey followed 2023 KQ-14 across a long enough observational arc to nail down its trajectory with unusual accuracy. The team integrated its motion forward and backward in time, using the most refined available models of the gravitational forces from the Sun and the known giant planets. They calculated as precisely as they could what 2023 KQ-14's orbit should look like. The orbit they found was almost too clean. What does it mean for an orbit to be too clean? In planetary mechanics, even a stable orbit is rarely perfectly smooth across long timescales. Gravitational interactions with other bodies, distant passes of stars during the early solar system's life in its birth cluster, even the slow accumulated effect of the galactic tide on long-period objects. All of these produce small distortions in the orbit. Over millions of years, the distortions add up. They show up in the orbital elements as small wobbles, small drifts, small fingerprints of past gravitational interactions. 2023 KQ-14's orbit shows almost none of those fingerprints. It looks like the orbit of an object that has spent its entire existence far from anything massive enough to leave marks. And that is where the tension with Planet 9 enters. If Planet 9 exists, in the form Batygin and Brown described in 2016, its orbit should bring it through a particular region of the outer solar system. Across 4.5 billion years, Planet 9 should have made some number of orbital passes, depending on its exact period, somewhere between 200,000 and 400,000 laps around the Sun. Each pass would carry it through a particular slice of the outer solar system, and during each pass, every object within a few hundred astronomical units of Planet 9's path would feel a brief gravitational tug. The tugs would accumulate over geological time, small at first, building, across millions and then billions of years, into measurable distortions in the orbits of nearby objects. Any object whose orbit brought it close to Planet 9's path, repeatedly, over the age of the solar system, would carry the cumulative fingerprint of those encounters. 2023 KQ-14 carries no such fingerprint. Its orbit is pristine. The interpretation Huang and colleagues offered was direct. If Planet 9 exists, it cannot be on the orbit Batygin and Brown originally proposed in 2016. 2023 KQ-14's pristine orbit constrains where Planet 9 can be. Specifically, Planet 9 must be either farther from the Sun than the early models assumed, or on a different orbital path that does not pass near 2023 KQ-14's region of the outer solar system. Either way, the search zone for Planet 9 has to be redrawn. This is not a fatal blow to the Planet 9 hypothesis. It is a constraint. It is a piece of evidence narrowing the possible orbital parameters of the proposed planet. It is the kind of result that, in a healthy scientific process, refines a hypothesis rather than destroying it. But it is a constraint with consequences. If Planet 9 is farther from the Sun than the early model said, it is even fainter. Its reflected sunlight, by the inverse fourth power, is even more diluted. Its thermal infrared signal, while less devastatingly diluted, is still weaker than the original models assumed. The signal-to-noise ratio of any search becomes more difficult. The fraction of sky that needs to be covered increases. The Rubin survey, when it finally arrives, has to be sensitive enough to detect a planet that may be sitting deeper in the dark than anyone had hoped. Let me invite you to spend a moment in your mind standing on the surface of 2023 KQ-14. The Sun is overhead, but it is not warm. It does not feel like a sun. It looks like a bright star, the brightest point in the sky, but it is not bright enough to read by easily, and it does not cast much of a shadow. The surface temperature where you are standing is around 20 Kelvin, more than 250 degrees below freezing. The ground beneath your feet is a kind of frozen rock and ice. There is no atmosphere. There is no wind. The sky is black. The other stars, distant and unwavering, sit in fixed positions in the cold black. The orbit you're on takes more than 10,000 years to complete. The path beneath your feet has been smooth for billions of years. Nothing massive has come near you recently. Nothing massive is near you now. The space around you is, in a precise physical sense, very nearly empty of anything that could push you around. You can feel, not in a poetic sense, but in a directly imagined sense, the absence of any nearby disturber. You're alone in your slow circuit around the Sun. The planet you're looking for, the unseen body that is supposed to be tugging on your orbit, is not here. It is somewhere else, somewhere farther, and your quiet orbit is the proof. This is what the data of 2023 KQ-14 tells us. The pristine orbit is a witness. It is an absence of evident statement, in the cleanest possible form. If Planet 9 is real, this is not where it is. The orbit is the silence in which we can hear what is not present. What 2023 KQ-14 does not do, however, is dissolve the broader case for Planet 9. Its own orbital orientation still falls within the family of orientations that motivated the Planet 9 hypothesis in the first place. The clustering pattern that started this search still includes objects like 2023 KQ-14. The pattern is intact. It is just telling researchers that whatever produced the pattern needs to be located more carefully than the original model assumed. The compass needles still point the same way. The source of the pointing is just farther away than the early model said. This is, in a meaningful sense, how science actually moves forward. Not in straight lines, but in a constant dialogue between prediction and constraint. Each new object discovered in the outer solar system is another data point either supporting the model, challenging it, or reshaping it. 2023 KQ-14 does the third. It accepts the broad framework while demanding more precision from the details. The existence of Planet 9 becomes harder to place, but it does not become harder to believe, and the sednoid population as a whole, sitting in its stable distant orbits, provides a kind of consistency check on the Planet 9 story. If Planet 9 exists on a very long, very slow orbit, it would spend most of its time at the far end of that orbit, far from the sednoids it once influenced. It would shape their orbits during the rare periods when it swung through their neighbourhood, then retreat back into the deep outer solar system, leaving them undisturbed for thousands of years at a stretch. The stability of the sednoids is not evidence against Planet 9. It is evidence for a Planet 9 that moves slowly enough and stays distant enough to let the objects it organise settle into quiet paths. The outer solar system in this picture is not a chaotic junkyard. It is an organised place, more organised than it has any right to be, given what we know about how solar systems form. Something sorted it, something with patience measured in billions of years, and whatever did the sorting has since retreated to a comfortable distance, leaving behind a collection of frozen worlds in stable orbits, pointing quietly and persistently toward a region of space where two faint infrared signals have already been detected and never explained. That picture, by 2025, has come into clearer focus. The pattern is real. The mechanism is at least partially constrained. The location of the unseen object, while still not pinned down, has been narrowed by every new piece of evidence. But there is one alternative to the Planet 9 hypothesis that needs to be taken seriously. An alternative that, if true, would mean that none of the indirect evidence we have been collecting will ever lead us to a planet at all. An alternative that would mean the object out there is something much stranger than anyone in 1990, when the search began in earnest, would have imagined. It would mean the object pulling on the outer solar system is not a planet, but a black hole. Part 9. The Grapefruit in the Dark. In 2019, two physicists published a paper in Physical Review Letters that, depending on who you ask, was either a legitimate scientific proposal or a deeply uncomfortable thought experiment that the Planet 9 community did not particularly want to entertain. The two authors were Jakob Schultz at Durham University in the United Kingdom and James Unwin at the University of Illinois at Chicago. The journal volume was 125. The article number was 051103. The title was, in its entirety, "What if Planet 9 is a primordial black hole?" The paper's argument was simple in form and unsettling in implication. Schultz and Unwin pointed out that all of the indirect evidence collected for Planet 9 over the previous several years, the orbital clustering, the 6-degree solar tilt, the stability of the sednoids, the retrograde outer system population, even the Akari infrared candidates, if you stretch the interpretation, was indirect gravitational evidence. The pattern in the data was a pattern in how distant objects move under the influence of a hidden mass. Gravity, at long range, cares only about the mass of the source. It does not care about the source's composition, its size, or its shape. A 10 Earth mass planet and a 10 Earth mass black hole would pull on surrounding objects in exactly the same way. The same orbital clustering, the same 6-degree torque on the planetary plane, the same stable sednoid alignments. Every piece of indirect evidence in the Planet 9 case is consistent equally well with a planet of the predicted mass, and with a black hole of the same mass, and as of 2019 there was no observational test that could distinguish between the two. Let me try to land what a black hole at that mass would actually be like, because the size of it is shocking. The radius of a Schwarzschild black hole, the size of its event horizon, the boundary inside which not even light can escape, scales linearly with the black hole's mass. The Schwarzschild radius is 2 times Newton's gravitational constant times the mass, divided by the speed of light squared. Run the numbers for a black hole of 10 times Earth's mass. The Schwarzschild radius comes out to approximately 9 centimetres. 9 centimetres, about 3.5 inches, about the size of a grapefruit-sized object, not a grapefruit-sized planet, a grapefruit-sized singularity, a region of space so warped by mass that not even light escapes from its surface. compressed into a sphere you could hold in one hand and carrying the gravitational pull of nearly 10 Earths. The strangeness of this is worth dwelling on for a moment. If you somehow approach such an object, you would not see it. There is no surface to reflect light. The event horizon, the boundary of the black hole, absorbs everything that crosses it and emits essentially nothing. The space immediately outside the horizon would be a region of severely distorted space-time, where distant starlight would bend visibly around the object and produce a kind of dark distortion at the centre of your field of view. But the black hole itself, as a thing you could detect, is invisible by every method that the Planet 9 search has so far employed. It would emit no reflected sunlight, because there is no surface. It would emit no thermal infrared radiation in the conventional sense, because there is no body of warm material to radiate. Hawking radiation, the quantum effect by which black holes emit a tiny trickle of thermal radiation from the vicinity of their event horizons, exists for any black hole, but for a black hole of 10 Earth masses, the Hawking temperature is so low and the resulting emission so weak that it is completely undetectable across the distances involved. It would be invisible. The orbital clustering pattern in this picture would still be there. The 6-degree tilt would still be there. The sednoid stability would still be there. Every piece of the indirect case for Planet 9 transferred unchanged. The Akari infrared candidates, if they exist as real signals, would not be the primordial black hole. Black holes do not produce that kind of thermal emission. The Akari candidates would, in this picture, be either background contamination or a different solar system body, leaving the actual perturber undetected. Primordial black holes themselves remain a theoretical proposition. Stephen Hawking, in a paper published in Monthly Notices of the Royal Astronomical Society in 1971, was the first to propose that black holes could have formed during the extreme density conditions of the early universe, in the first fractions of a second after the Big Bang, before stars or galaxies existed. The very early universe contained regions of extraordinarily high density, and Hawking argued that some of those regions could have collapsed directly into black holes of various masses, depending on the size of the collapsing region. Primordial black holes of certain mass ranges have been proposed as candidates for part of the universe's dark matter, the invisible mass that holds galaxies together, but has never been directly detected by any other means. Other mass ranges have been excluded by various observational constraints. The mass range relevant to a Planet 9 candidate, a few Earth masses up to perhaps 100 Earth masses, sits in a region that is allowed by current constraints, but has never been confirmed by direct detection of an actual primordial black hole. Schultz and Unwin worked out the math of how many such primordial black holes might exist in the local neighbourhood of the Sun, integrated over the volume the early solar system would have swept through during its formation. The numbers they got suggested that capture of such an object during the Sun's life in its birth cluster is at least plausible. Not likely, not predicted, but plausible enough to take seriously as a possibility. What the paper did, in the broader community, was force a reckoning with an uncomfortable truth. The indirect gravitational evidence for Planet 9, all of it, every piece gathered over a decade of careful work, cannot distinguish between a planet and a black hole of the same mass. The two possibilities are gravitationally identical from the outside, and the only way to tell them apart is to find the object and observe it directly. Finding something that emits no reflected light, no significant thermal radiation, and no signal of any kind requires either extraordinary luck with a gravitational microlensing event or a level of precision in the search that current technology has not quite reached. There is a method by which a primordial black hole could in principle be detected: microlensing. When a massive object passes between Earth and a distant background star, its gravity bends the starlight around it, producing a brief brightening of the star as seen from our position. This effect, called gravitational microlensing, is a well-established technique already used to search for compact dark objects across the galaxy. Surveys like the Optical Gravitational Lensing Experiment, OGLE, have been monitoring millions of stars in the galactic bulge for years, looking for microlensing events that would reveal the presence of compact dark objects. A primordial black hole slowly drifting through the outer solar system on a long Planet 9-like orbit would in principle produce microlensing events as it crossed in front of background stars. The events would be rare because the angular sizes involved are small and the alignment required is precise. The events would be brief because the lens motion is slow but the geometric alignment window is narrow. The events would be faint because the lensing amplification at this mass and distance is modest, but they would not be impossible. If a dedicated microlensing survey were aimed at the predicted region of sky for long enough, and a primordial black hole of the right mass was sitting in that region, a microlensing event could in principle be detected. As of 2025, no such event has been confirmed in the predicted region. This is not strong evidence against the primordial black hole interpretation, because the survey time and sky coverage required to detect such a rare event have not yet been fully invested. The negative result is consistent with both possibilities, so let me invite you to do a particular kind of imaginative work for a moment. Hold out your hand, palm up. Imagine that you are holding a grapefruit. Feel its weight, its size, its rough texture. Now imagine that the grapefruit is not a grapefruit. It is a black hole, a region of space so dense that nothing escapes its surface, containing the mass of 10 Earths, held, in this imaginary moment, in the palm of your hand. Now imagine taking that grapefruit and placing it somewhere out beyond Neptune, in the cold and dark of the outer solar system, on a long elliptical orbit that takes 10 or 20,000 years to complete one lap around the Sun. The grapefruit sitting in the dark with nothing visible around it, gently bending the orbits of frozen worlds across hundreds of astronomical units. The same bending it would do if it were a 10 Earth mass planet, indistinguishable from a planet by every piece of gravitational evidence we have ever collected. That is the grapefruit in the dark. The emotional weight of this picture is not the strangeness of the object itself. It is the realization of what it means about the search we have been running. For 9 years, the Planet 9 community has been hunting for a planet. The implicit assumption has been that the object responsible for the orbital anomalies is a body with a surface, a body that reflects light, a body that emits thermal radiation, a body that can in principle be photographed by a sufficiently sensitive telescope at the right wavelength. Schultz and Unwin's paper said, maybe none of that is true. Maybe the object we have been chasing is the kind of object that no telescope can photograph, because there is no surface to photograph. Maybe the long, careful infrared searches, the patient optical sky surveys, the decade of work and ingenuity are aimed at the wrong kind of target. Maybe the indirect evidence we have spent 10 years building is silent on the most important question, whether the cause is a planet or something far stranger, and the silence will only be broken by an instrument capable of detecting a microlensing event, or by some other entirely different kind of search, a relic of the first instant of the universe, formed in the first fractions of a second after the Big Bang, captured by the young solar system in some long-ago dynamical encounter, sitting in the outer dark for billions of years, silently shaping the orbits of frozen worlds for the entire history of life on Earth. That is the alternative possibility, a fossil of conditions that predate the stars themselves, sitting in our own backyard, leaving the same marks a planet would leave. The evidence we have cannot tell us which it is. There is one more layer of complication. Even setting aside the primordial black hole alternative, even granting for the sake of argument that the object out there is a planet, there is a serious scientific challenge to the very foundation of the search. A challenge that asks whether the pattern in the data, the 6 compass needles all pointing the same way, the entire statistical case that motivated 9 years of work is even real at all. Or whether it might be a kind of mirror, a reflection of how astronomers have been looking, more than what is actually out there. That challenge is worth taking seriously, because if it is correct, the entire Planet 9 question collapses, and if it is incorrect, the case for Planet 9 becomes substantially stronger than it currently appears, and the only way to settle it is exactly the kind of survey that the Vera Rubin Observatory was designed to do. Part 10. The Statistical Mirror. In 2019, the same year Schultz and Unwin published their primordial black hole paper, a different challenge to the Planet 9 hypothesis appeared in the literature. It came from a team led by Kevin Napier and David Gerdes at the University of Michigan, working with data from a large sky survey called the Dark Energy Survey. The Dark Energy Survey, or DES, was a 6-year astronomical project conducted from the Cerro Tololo Inter-American Observatory in Chile, the same general region of the Andes as the Rubin Observatory, but at a different mountaintop. Between 2013 and 2019, DES used a 570 megapixel camera mounted on a 4-meter telescope to map an enormous patch of the southern sky in deep optical wavelengths. The survey's primary goal was cosmological, measuring the large-scale structure of the universe to constrain the properties of dark energy. But because DES covered a wide swathe of the ecliptic with deep sensitivity over multiple seasons, it also produced a substantial catalogue of newly discovered outer solar system objects. Napier, Gerdes, and their collaborators took the DES outer solar system catalogue and asked a specific question. The question was not whether Planet 9 exists. The question was whether the original Batygin and Brown clustering analysis had properly accounted for the observational biases of the surveys it drew its sample from. This is a deep methodological point, and it deserves to be laid out carefully. Astronomy is not a uniform sampling of the universe. Telescopes are not pointed at the sky randomly. Observing time is allocated based on scientific goals, atmospheric conditions, instrumental sensitivities, scheduling constraints, and the personal preferences of the researchers running the surveys. Some patches of sky are observed more often than others. Some patches are observed at greater depth than others. Some orbital orientations of distant objects are intrinsically easier to detect than others, depending on the geometry of the observing platform and the brightness limits of the instruments. This kind of non-uniform sampling produces what astronomers call observational bias. It is one of the most persistent sources of systematic error in any survey-based science. If you do not properly account for the fact that your sample was preferentially drawn from certain regions of the search space, you can end up finding patterns in your data that reflect the structure of your observing strategy rather than the structure of the universe. The argument Napier, Gerdes, and their collaborators made was that the 6 original extreme trans-Neptunian objects whose clustering motivated the Planet 9 hypothesis had not been discovered through a uniform sky survey. They had been found in patches, through different surveys, motivated by different scientific goals, with different brightness limits and different sky coverages. The combined sample, when analysed without correction for these factors, appeared to show statistical clustering of orbital orientations, but when the team applied a rigorous mathematical correction for the actual observational footprint of the surveys that had discovered the objects, the apparent clustering signal weakened substantially. The intuition behind this is worth unpacking. Imagine that the outer solar system is filled with extreme trans-Neptunian objects whose orbital orientations are completely random. No clustering, no pattern, no Planet 9. The orbits are distributed uniformly across all possible orientations. Now imagine that astronomers have surveyed primarily certain regions of the sky, especially regions near the ecliptic at certain right ascensions, because that is where the observing schedule and the instrumental capabilities have aligned. The objects that get discovered preferentially are the ones whose orbits, at the time of observation, happen to bring them into the surveyed patches at the right brightness for detection. If the underlying population is uniform, then the discovered sample is skewed by the survey's observing footprint. Certain orbital orientations are more likely to be discovered, because those orientations bring the objects through the surveyed regions when they are brightest. The discovered objects will appear to share certain orbital orientations, not because the underlying population has those orientations, but because the survey systematically missed objects with different orientations. The result is an apparent clustering pattern in the discovered sample that does not reflect a real clustering pattern in the actual population. It is a survey selection artifact. It is the survey's footprint projected onto the data, mistaken for a feature of the underlying solar system. Napier and Geddes argued that exactly this kind of artifact could explain the apparent clustering of the original 6 objects. They showed, using the Dark Energy Survey's own well-characterized observational footprint, that the survey's detection efficiency varied substantially with orbital orientation, and that after correcting for this variation, the DES sample of extreme trans-Neptunian objects was statistically consistent with a uniform distribution. The clustering in the corrected sample was much weaker than the original Batygin and Brown analysis had reported. If this analysis is correct, the implication is far-reaching. The original case for Planet 9, the 1 in 14,000 probability, the 6 compass needles all pointing the same way, is not a feature of the solar system. It is a feature of how human astronomers have searched the sky. The pattern is real in the sense that the discovered objects do share certain orbital orientations, but the cause of the pattern is not a hidden planet shepherding the orbits of distant worlds. The cause is the inhomogeneous coverage of past surveys. The hand on the scale is not Planet 9, it is us. There is no anomaly to explain. The outer solar system is behaving exactly as an empty, unorganized region should. The orbital clustering is an artifact of how humans searched, not a reflection of what the solar system actually contains. Planet 9, in this scenario, was conjured from a statistical illusion, a remarkably compelling one, but an illusion nonetheless. This is a serious challenge. It does not depend on questioning the basic data of any survey. It does not require attributing error to any individual measurement. It is a challenge at the level of methodology, at the level of how one extracts a population-level claim from a non-uniform sample. And that level of challenge is the kind of challenge that, if it holds up, dissolves the original case rather than refuting it. The Planet 9 community pushed back. Batygin, Brown, and their collaborators argued that even with rigorous bias corrections applied, a statistically meaningful clustering signal survived. The pattern weakened under correction, they acknowledged, but it did not vanish, and the residual signal still required an explanation that random chance could not comfortably provide. They produced their own bias-corrected analyses using different statistical methods that preserved a clustering signal above the random chance threshold. The debate has not been resolved. Different teams, using different bias correction methods on different subsets of the available data, continue to reach different conclusions. Some methods find a residual clustering signal that demands explanation. Others find that the signal dissolves almost entirely once the survey's observational footprints are properly accounted for. The honest summary of where the field stands as of 2025 is that the statistical foundation of the Planet 9 hypothesis is contested, not debunked, not confirmed, but genuinely uncertain in ways that the 2016 Batygin and Brown paper did not fully anticipate. What this means in practice is that every piece of indirect evidence for Planet 9, the orbital clustering, the solar tilt, the sednoid alignments, even the retrograde outer system objects, carries an asterisk. Each piece of evidence is real in the sense that the observations themselves are real. The orbits exist, the tilt exists, the objects exist. But whether the patterns we read into them reflect a genuine feature of the solar system or a feature of how we have explored the solar system is a question that the existing data cannot definitively answer. The tool used to draw the map may have introduced distortions into the map itself. This is not a failure of science. It is science working exactly as it should. A hypothesis makes predictions. The predictions attract scrutiny. The scrutiny reveals methodological weaknesses. The weaknesses demand better data. The entire trajectory of the Planet 9 debate, across 9 years of indirect evidence and contested statistics, and infrared candidates and competing theories, has been pushing toward one specific outcome: a sky survey thorough enough and unbiased enough to test the clustering pattern against a complete evenly sampled data set. A survey that does not look harder in one direction than another. A a survey that covers the whole sky with the same depth and sensitivity everywhere. That survey is now running. The Vera Rubin Observatory is exactly that survey. Its design eliminates the bias problem by construction. The same instrument visits the same patches of sky at the same depth and the same cadence everywhere across the accessible sky. There is no preferred direction. There is no preferred orbital orientation. When the Rubin catalogue of distant outer solar system objects grows large enough, and it will grow far larger than any previous survey, the clustering pattern will either survive the statistical test or it will not. There will be no ambiguity about the survey's coverage. There will be no argument about whether the bias corrections were applied correctly. The data will be as clean as ground-based astronomy can produce. If the clustering survives, if the aligned orbits remain statistically significant in a dataset built without the selection effects that haunted earlier surveys, then the case for Planet 9 becomes substantially harder to dismiss. The skeptics will have been answered on their own terms. The pattern will be real, the hand on the scale will not be us, and the only remaining question will be what kind of hidden mass is producing the pattern. If the clustering dissolves, if the pattern flattens out into randomness when measured against a complete and unbiased sky, then the field will face a reckoning. A decade of models, predictions, and searches will need to be reassessed from the ground up. The 6 compass needles will turn out to have been pointing the same way, mostly because we were looking in the same direction. Either outcome moves science forward. That is the thing about a well-designed test. It cannot produce a useless result. A confirmation strengthens the case. A non-detection clears the air. Both answers are worth having. Both answers have been a long time coming. And for the first time in the history of this search, the instrument capable of delivering one of them is already open and watching the sky. Part 11. Why Rubin Settles. It returned to the mountain. Cerro Pachon sits in the Coquimbo region of northern Chile, at the southern end of the Andes' driest stretch. The air at the summit is exceptionally clear, exceptionally dry, and exceptionally stable. The number of nights per year suitable for high-precision astronomy is among the highest of any observatory site on Earth. The Vera Rubin Observatory shares the mountain with several other large telescopes. This site is one of the most densely instrumented patches of high-altitude land in the southern hemisphere. The Simony Survey Telescope, the optical assembly at the heart of the Rubin Observatory, was designed from the outset for a single purpose: to perform a comprehensive 10-year survey of the entire accessible night sky in optical wavelengths, with revisit times short enough to detect any kind of moving or varying object. The Legacy Survey of Space and Time, or LSST, is the name of that 10-year program. The telescope and the survey were designed together as a single integrated instrument. Every aspect of the design serves the survey. The mirror is unusually large for its focal length, because the survey demands a wide field of view that conventional long focal length telescopes cannot deliver. The optical system is unusual. 3 mirrors in a folded design, optimized for image quality across the entire 10 square degree field. The camera is unprecedented in size, because the survey demands that the wide field be sampled at high resolution across the full focal plane. The data handling pipeline, perhaps the least visible but most essential component of the whole system, is designed to compare each new image automatically against all previous images of the same patch of sky, and to flag every change in real time. The cadence is the design decision that matters most for the Planet 9 search. The Rubin survey visits each patch of accessible sky approximately every 3 nights, on average, throughout the 10-year survey. Some patches are visited more often, some less, but every region of the accessible sky is observed dozens to hundreds of times over the survey lifetime, in multiple optical filter bands, under varying atmospheric conditions. What that cadence enables, for a search like Planet 9, is the detection of slow motion. Planet 9, at the predicted distances of 400 to 700 astronomical units, or possibly farther after the 2023 KQ-14 constraint, would move very slowly against the background stars. Its apparent motion across the sky, called proper motion in astronomical terms, would be on the order of a few arcseconds per year. That is small. It is smaller than the typical seeing of ground-based astronomy. It is smaller than the daily atmospheric refraction variations, but it is not zero. Over a year, Planet 9 would move by a measurable amount. Over 10 years, the accumulated displacement would be large enough that an automated pipeline comparing images taken months and years apart would detect the slow drift unambiguously. Whatever orbital path Planet 9 is on, if it is anywhere within the predicted distance range and not directly behind the densest star fields of the Milky Way, the Rubin pipeline will detect its slow apparent motion during the survey's lifetime. The same pipeline detection works for any planet mass object across the predicted distance range. It does not depend on the object being at a particular orbital phase. It does not depend on the object being in any particular constellation. It does not depend on the object being brighter than some specific magnitude threshold, beyond the basic detection flaw of the survey. Whatever combination of position, orbital geometry, and brightness the object has, if it is detectable at the survey depth and visible from the southern hemisphere, Rubin will see it. The same architecture solves the bias problem that haunted earlier searches. Because Rubin visits every part of the accessible sky at the same depth, with the same cadence, using the same instrument, the catalogue of newly discovered outer solar system objects will be statistically uniform in a way that no previous catalogue has been. The kinds of objects detected will reflect the underlying population, not the structure of the observing strategy. The clustering pattern that motivated the Planet 9 hypothesis can be tested directly against a clean, unbiased sample. If the pattern is real, it will survive in the Rubin catalogue. If it is an artifact of how previous surveys looked, it will dissolve. Picture, again, a clear Tuesday night in the southern Chilean spring. The dome opens at twilight. The mirror is at temperature, the camera is at temperature. The operators are checking the night's observing plan. The first exposure of the night is taken on a patch of sky in the constellation Hydra, perhaps, or Centaurus. 15 seconds open. The telescope slews to the next patch. Another 15 seconds open, then the next. The pattern repeats. The whole accessible sky gets sampled across a few nights of operation. Each image flows down off the mountain, through fibre optic cables, into a network of data processing centres spread across the United States and France and Chile. The images are calibrated. They are compared against the survey's master reference images. Every point of light is checked against the catalogue of known objects. Anything new, a new star, a new transient, a new moving body, gets a flag. Anything that has moved since the last visit gets a flag. By morning, thousands to millions of flagged sources have been added to the alert stream. Somewhere in those flagged sources, eventually, may be the answer. The first signal of Planet 9 in the Rubin data, if Planet 9 is real and is bright enough to be detected, will not be a dramatic image. It will be a few faint pixels on a CCD, drifting slowly across the sky between visits. An automated pipeline will flag it. A team of human astronomers will follow up. The follow-up will involve checking the candidate against deeper images, computing its preliminary orbit, comparing the orbit against the predicted parameter space for Planet 9, and verifying that the photometric properties, the brightness in multiple filter bands, match what Nice Giant at the predicted distance would produce. The process from initial flagging to confirmed detection might take weeks or months. When the confirmation arrives, if it arrives, the announcement will be the largest in planetary astronomy in a generation, a 9th planet in our own solar system, a super-Earth mass ice giant exiled to the outer dark, found at last after a decade of indirect argument and patient searching, by an automated camera on a Chilean mountain, photographing the sky on a quiet, ordinary night. But the same survey that would announce the detection would also announce the alternative, if the alternative is what is true. If the survey runs for its full 10 years and turns up no candidate consistent with Planet 9 across the accessible distance range, the non-detection will be a definitive statement. The original Batygin and Brown 2016 model, in its strongest form, will be ruled out. The compass needles will not be being pointed by a planet of the predicted mass and distance, and in that case, the field will pivot. The primordial black hole alternative will move forward as a leading candidate. The microlensing surveys will be expanded and refined. The bias correction debate will effectively be resolved by the Rubin data itself. If the clustering pattern dissolves in the unbiased sample, the Napier and Gerdes interpretation wins. The modified gravity alternatives will receive renewed attention as ways to explain the apparent anomalies without requiring a hidden body of any kind. The retrograde outer system population will need a different explanation than the long-inclined Planet 9. The 6-degree solar tilt will return to its previous status as an unresolved anomaly without a clean explanation. The compass needles will still be there. The pattern in the data, weakened but not erased, will still need to be reconciled with whatever is or is not in the outer solar system. But the search for a planet specifically will be over, and the question will have changed shape. What Rubin gives the field, in either outcome, is a clean answer to a question that has been answered ambiguously for a decade. That is the value of a well-designed instrument paired with a well-designed survey. It does not promise the answer the searchers want. It promises only that the answer it produces will be reliable. There are two ways this can go. We need to walk through them carefully, because the consequences of each are significant. Part 12. The two outcomes begin with the scenario in which Rubin finds it. A confirmed detection of Planet 9 by the Rubin survey would arrive most likely sometime in the next 3 to 7 years, depending on where exactly the planet is sitting relative to where the survey has already looked. The detection itself would begin as a small set of flagged sources in the alert stream, points of light that have moved slightly between observing epochs, consistent with the slow, proper motion expected of an object at hundreds of astronomical units. Within weeks of the initial flagging, follow-up observations using deeper exposures and additional filter bands would refine the candidate's brightness, colour, and preliminary trajectory. Within months, the orbit would be characterised well enough to confirm that the candidate matches the parameter space predicted for Planet 9. The scientific announcement would follow. The paper would likely be authored by the discovery team within the Rubin collaboration, with co-authors from across the Planet 9 search community, whose decade of indirect evidence and orbital predictions had set up the discovery. The reaction across planetary astronomy would be immediate and global. Every observatory with relevant capabilities would redirect resources toward the confirmed location. The James Webb Space Telescope, the most sensitive infrared observatory ever built, would be retargeted within weeks. JWST has the infrared sensitivity to study Planet 9 in detail at the predicted distance range. Directors' discretionary time would be allocated to follow-up observations. The first detailed infrared portrait of the world would be built up over a series of JWST observations spanning multiple months. Spectral measurements would constrain the planet's atmospheric composition. The first estimates of its rotation period would emerge from the photometric variations as different surface features rotated in and out of view. Ground-based telescopes across both hemispheres would begin the long process of precisely mapping the planet's orbit. Once the orbital elements are pinned down to high precision, the planet's complete trajectory across the next several thousand years could be calculated. Its mass would be refined through gravitational analysis of the orbits of nearby trans-Neptunian objects. Its composition would be inferred from its colour, its infrared emission, and any spectral features detected by JWST. A new chapter of solar system science would open within months of the announcement. The discovery would force a fundamental rewrite of how the early solar system is understood to have formed. The current models, built around 4 rocky inner planets and 4 giants arranged through a specific sequence of gravitational interactions and migrations, would need to accommodate a 5th giant. The Nice model, which describes the migration of the giant planets and the sculpting of the Kuiper belt during the first few hundred million years of the solar system, would need significant revision to include a planet that was ejected from the inner regions and recaptured into a long-distant orbit. The implications for exoplanetary statistics would also be enormous. Most of the planets discovered around other stars to date have been intermediate in mass between Earth and Neptune, the so-called super-Earth and sub-Neptune class. These are statistically the most common kind of planet in the galaxy. The absence of any such world in our own solar system has been one of the persistent mysteries of planetary statistics. Why is our solar system missing the most common kind of planet? Planet 9, if confirmed, would fill that gap. Our solar system would no longer be unusual for lacking a super-Earth. We would simply have one, sitting in an orbit that took us a long time to find. That would make our solar system a much more representative example of what planetary systems look like across the galaxy. The frequency with which planets get scattered into distant orbits, the frequency with which solar systems retain their most common planet type in unusual configurations, the long-term dynamical evolution of the multi-giant systems, all of these questions would gain a local data point. Now turn to the alternative scenario. Rubin completes its full 10-year survey. No candidate consistent with Planet 9 emerges across the accessible distance range. The non-detection is definitive. The original Battagin and Brown 2016 model, in its strongest form, is ruled out. What follows is a different kind of scientific event. There is no single announcement. There is instead a gradual recognition across the planetary astronomy community that the search has failed to produce its target, combined with rigorous statistical analyses of exactly what the non-detection constrains. The first consequence is that the orbital clustering pattern, if it was real at all, was not produced by a planet of the predicted mass and distance. The Napier and Gerdes bias correction analysis, in this scenario, effectively wins the methodological debate. The clean, unbiased Rubin sample would show whether the clustering survives in a properly sampled population. If the Rubin sample preserves the clustering, then Planet 9 in some other form is still required to explain it. If the Rubin sample does not preserve the clustering, the original case is dissolved. The second consequence is that the primordial black hole alternative moves to the front of the conversation. If Planet 9 is invisible to the most comprehensive optical survey ever conducted, and the indirect gravitational evidence still requires some hidden mass at hundreds of astronomical units, the missing planet may not be a planet at all. The grapefruit in the dark. A dedicated microlensing search of the outer solar system, looking for the rare alignment events that would reveal a compact dark perturber, becomes the next phase of the search. Such a search would take additional decades, but it would proceed with the knowledge that the planetary alternative has been ruled out. The third consequence is that modified gravity at extreme distances receives renewed attention. If no body of any kind is producing the apparent anomalies, perhaps the anomalies are not produced by a body. Modified Newtonian dynamics, originally proposed by Mordechai Milgrom in 1983, predicts deviations from standard gravity at very weak accelerations. In the inner solar system, accelerations are far above the Mond threshold, and standard gravity works exquisitely. In the outer solar system, at hundreds of astronomical units, the gravitational acceleration from the Sun begins to approach the threshold. Whether the threshold is crossed depends on the precise formulation, but the regime is at least plausibly relevant. A Rubin non-detection would leave a cleaner space for modified gravity proposals to be tested against the actual orbital data. The fourth consequence is the distributed mass hypothesis. Perhaps the orbital anomalies are produced not by a single large hidden body, but by the combined gravity of many small undetected bodies in the outer solar system. If the trans-Neptunian population extends to smaller and fainter objects than current surveys have catalogued, their combined gravity could in principle mimic the effect of a single larger perturber. The Rubin survey itself, in producing the deepest, most comprehensive catalogue of outer solar system objects ever assembled, would partially constrain this hypothesis. If the Rubin catalogue does not contain enough total mass in newly discovered small bodies to explain the apparent anomalies, the distributed mass hypothesis is constrained. If it does, the anomalies have an explanation that does not require any single hidden planet. All of these outcomes, the primordial black hole becoming the leading candidate, The dedicated microlensing campaigns being launched, the modified gravity alternatives receiving renewed attention, the distributed mass hypothesis being tested against the Rubin catalogue, represent forward motion in science. None of them is empty. All of them produce new questions and new programs of research that would not have existed without the Rubin non-detection. The grapefruit in the dark in this scenario is not just an alternative possibility. It is the possibility that the non-detection actively points toward. A non-detection of a planet does not make the indirect evidence go away. The orbital clustering, the 6-degree solar tilt, the sednoid stability, the Akari infrared candidates, all of these would still need an explanation. If the explanation is not a planet, the explanation must be something stranger. The grapefruit in the dark moves from being an unusual alternative to being a candidate that the search itself is pointing at. Sit with both outcomes for a moment. Neither is empty, neither is unimportant, neither is a failure. A detection means our solar system has a 9th planet, hidden in the outer darkness for the entire history of human astronomy, and we have finally seen it. A rewrite of solar system formation models, the discovery of our missing super-Earth, the local example of the most common kind of planet in the galaxy, a discovery so consequential that it would be the largest single announcement in planetary science in our lifetime. A non-detection means the explanation for the orbital anomalies is something other than a planet of the predicted mass. The case for a primordial black hole, with all its strangeness, becomes substantially stronger. The microlensing campaigns begin, the relic of the first instant of the universe, captured by our solar system long ago, becomes the leading candidate for what has been organizing the outer solar system, or the modified gravity alternative, or the distributed mass alternative, or some other explanation entirely. Each of these becomes more plausible and more rigorously testable in the wake of the non-detection. The mystery does not collapse with the non-detection. The mystery widens, and in either case, the resolution arrives within the lifetime of the people who began the search. That is the rarest and most striking aspect of this entire story, and it is worth landing on directly. Because most scientific questions outlast the scientists who pose them. Most arguments in planetary astronomy run for decades or centuries, with each generation refining the question slightly and passing it on to the next. The Planet 9 question is different. The Rubin survey runs for 10 years. The astronomers who started this search in 2014, 2016, 2019, Batygin, Brown, Trujillo, Shepard, Bailey, Morbidelli, Fan, Goto, Huang, Schultz, Unwin, Napier, Gerdes, and dozens of others, are still working. They will be the first to see the answer when it arrives. The generation that proposed the planet is the generation that will learn whether it exists. That is rare in science. By a thin margin of luck and instrument timing, the question and the answer will share a generation. You're sitting at the moment that becomes true. Part 13. The patience that has been watching back. Step back for the closing of the story and consider what has accumulated. There are 2 faint points of infrared light sitting in a Japanese satellite archive that has been public since 2010. They have been sitting there in the data since the Akari satellite recorded them in 2006 and 2007. They have apparent positional motion consistent with what a distant cold solar system object would produce across a 23-year baseline. They have temperature signatures consistent with what a 10 Earth mass ice giant at the predicted distance would emit. They have survived a rigorous cross-elimination filter against every major published catalogue of stars, galaxies, asteroids, and comets. Neither one has been confirmed, neither one has been ruled out. There is a population of distant frozen worlds whose orbits all point through the same region of the sky. 6 of them in the original sample, with more added as subsequent surveys have produced new detections. Their alignment by the original calculation would happen by random chance only once in 14,000 random configurations. The pattern's statistical strength is contested. The pattern's existence is not. There is a 6-degree tilt of the entire planetary orbital plane relative to the Sun's equator. The tilt has been visible to anyone with a clear night and patience since the invention of astronomy. It is present in every star chart ever drawn, every painting of the night sky, every photographic plate exposed across the 20th century, every digital image captured by every telescope of the 21st. It sits, silently, in every observation humanity has ever made. The tilt has had no satisfying explanation for decades. The Bailey, Batygin, Brown calculation showed in 2016 that a long-inclined planet at hundreds of astronomical units would naturally produce it across 4.5 billion years of slow torque on the inner planets. There is a population of high inclination and retrograde outer system objects whose orbits run backwards through the solar system, at angles approaching the perpendicular to the planetary plane. The standard formation model does not produce these in the observed numbers. A long-inclined planet at the right mass and distance would naturally pump some scattered disk objects into such orbits over billions of years. There is a new sednoid, 2023 KQ-14, whose orbit is too clean to fit early Planet 9 models. Its pristine path constrains the predicted location of Planet 9. It does not erase the case, it adjusts the case. It pushes the search zone outward. There is a primordial black hole alternative that says the object we have been chasing for 9 years may not be a planet at all. Maybe a relic of the first instant of the universe, formed in the first fractions of a second after the Big Bang, captured by our solar system long ago. Maybe a grapefruit-sized point of impossibly dense mass, sitting in the outer dark, gravitationally indistinguishable from a planet, leaving the same marks for the same reasons. There is a statistical bias correction debate that asks whether the entire pattern is real or whether it is a reflection of how astronomers have searched the sky. The debate is unresolved between methods that preserve a residual signal and methods that erase it. The cleanest possible test of the question is a sky survey conducted with uniform depth and cadence across the accessible sky, with no preferred direction. That survey, the Vera Rubin Observatory Legacy Survey of Space and Time, is now running. The first full operational year was 2025. The first significant Planet 9 results will likely begin to emerge sometime in the next several years. The complete 10-year survey will be done by the mid-2030s. By that point, either Planet 9 will have been confirmed and characterized, or it will have been ruled out as a planet of the predicted mass and distance, and the search will have pivoted to the alternative explanations. You're sitting inside the last decade of an argument that has been alive for 9 years, and may be alive for 10,000 years. The early astronomers who looked up at the night sky in ancient Sumer and Babylon, who tracked the slow drift of the planets across the constellations, who first noticed that the wandering stars moved differently from the fixed ones, those astronomers were already, without knowing it, looking along an orbital plane that was tilted by 6 degrees from where it should have been. The fingerprint of the unseen object, if it is real, has been visible to anyone with eyes for as long as humans have looked up. We are the generation that is finally going to read it, or we are the generation that is finally going to understand that the fingerprint was an illusion, and that the cause of the apparent pattern was something quieter and stranger than a planet. Perhaps a hole in our understanding of gravity itself, perhaps a relic of the early universe, perhaps a methodological artifact in how we have searched the sky. Whichever answer arrives, it is going to arrive in the same lifetime as the people who first articulated the question in 2016. That is a kind of grace that science rarely provides. Most questions outlive their askers. This one will not. There is something quiet and almost ceremonial about the moment. A telescope on a Chilean mountaintop, photographing the southern sky every night, building up a record of every point of light visible from its location. The mountain itself is older than the question. The telescope is younger than the question by less than a decade. The data is being recorded. Picture the night, one more time. The dome is open. The mirror is at temperature. The camera is at temperature. The 15-second exposures are running. Somewhere in the southern sky, perhaps in a constellation you can see from your own backyard on a clear southern hemisphere night, The patch of sky containing whatever is or is not out there is being recorded tonight. The data is flowing down off the mountain through the fiber optic cables, into the data centers, through the pipelines, into the alert streams. The comparisons are running, the flags are being set. If there is something there, it is being recorded now. The recognition will come later, tomorrow or next week or in 3 years, depending on how quickly the pipelines surface the relevant detection and how quickly the follow-up observations confirm it. But the recording is now. If there is not something there, the recording of the absence is also now. The patch of sky that contains no Planet 9 is being added to the survey's accumulated coverage. The non-detection is being built up, exposure by exposure, into a constraint on what cannot be there. Either way, the answer is being written tonight. Not by a human astronomer making a discovery in a moment of insight, by a quietly humming machine for noticing change, photographing the sky over and over, comparing every image against every previous image, flagging every shift, every motion, every faint, slow drift. The patience of the survey is not human patience. It is mechanical patience. It is the patience of an instrument that does not get tired, that does not lose interest, that does not miss a night, that does not look in the wrong direction. The pattern in the outer solar system has had 4.5 billion years to settle into its current shape. The patience that produced it, whatever the cause, is geological. The instrument that is finally going to read it is matched to the geology, running long enough, sampling deeply enough, covering completely enough to find an answer if there is one to find. The pattern is real. Whether the cause is a planet or a primordial black hole, or a flaw in our gravitational theory, or an artifact of how we have surveyed the sky, the strangeness of the cause continues to outpace the strangeness of the mystery. Whatever the Rubin survey eventually finds, the answer will be more remarkable than what we were searching for. The signals are real, the numbers are real. The patience that has been watching the outer solar system for 4.5 billion years is finally being watched back. The search is almost over. Whatever is out there has been waiting long enough.